These are the examples for Geometry B, Credit 5, Lesson 21.1. Lesson 21.1, we're going to be getting into set theory and also probability. And so let's go ahead and jump into it. So we have up on the board examples for the first page, page 14, problems 1 to 7. So we have, let's start down here. We have a universal set. And what a universal set means is that for this problem, our entire universe, so it kind of means like it is what it sounds like, is just these 8 numbers. So our universal set is 1, 2, 3, 4, 5, 6, 7, 8. Now up here we have a bunch of subsets, and a subset just means that every set here, the numbers are contained in the universal set. So we have the set A, which is 1, 2, 3, 4, set B, which is 1, 3, and 5, set C, which is 3, 4, and 5, and set D, which is 6, 7, and 8. So notice everything in all 4 of those sets are numbers that you can find in the universal set. And so let's go ahead and jump into the work and see how we do these problems. So our example for number 1, we have A, and we have what looks like a upside down U there. And so that's the symbol for intersection. And intersection means what numbers are in both sets. So A intersected B means what numbers, what elements, if you will, are in both sets. Well, let's take a look. 1 is 1 in, here's A and here's B. 1 is in both sets, so we would include that. We're going to use the set brackets here. Let's see. 2 is not in both sets, so we won't write it. 3 is in both sets, so we'll include 3. 4 is not in both sets. And that's really all you have to do, because if you check all the numbers from one of the sets to see if that number is also in the other set, then you'll cover everything. You'll get all the numbers that are in both sets. Because you say, well, what about 5? Well, we don't have to check 5 because it wasn't even in set A. So A intersected B would just be the elements or numbers 1 and 3, because 1 and 3 are the numbers that are in both sets A and B. All right, let's do another intersection problem. This time it's B intersected C. And so let's go ahead and do that and go through the elements of B and see which ones are also in C. So 1, nope, no 1 over here in C. 3, yes, 3 is in C, so we'll include that. And what about 5? Yes, 5, because 5 is in both sets. And that's it. So our answer there is 3 and 5. And that's all the work you have to do. And that is it. All right. So now what about our next one, C intersected D? So 3, is 3 in both sets? Nope, 3, no 3 over here. 4, nope, no 4 over here. What about 5? Nope, no 5 over there. So there are no elements in the intersection. So we say that's an empty set. And there's 2 ways you can represent that, is with a circle with a line through it, or you can just draw the set brackets and literally just leave it empty. Notice this is something I need to clarify. This is not 0. So and you wouldn't put the set brackets, you would not put this, well, I guess you could, but you wouldn't put both of these. It's one or the other. You wouldn't put 0 in here, because you might think, well, 0, that means nothing, right? Well, 0 though is a number. So if you put a 0 in here, you're saying that there's a 0 in both sets C and D, and there's actually there's not a 0 in either set. So again, 2 ways to represent an empty set. Sometimes it's called a null set, N-U-L-L. Let's go ahead and write that out. Empty or null set. You can just say empty set. And 2 ways you can represent it: the circle with a line through it, or the set brackets and just leave it blank inside. All right, so that's it for intersection. As we always say, pause, rewind the videos. Let's go to our next set of problems, or a couple of problems here. We're talking about union. So this is A union B. So now the U is upright, if you will, and it does stand for union. And so union means we're uniting the sets. We're bringing the two sets together. Every element that's in either set we're going to include. And we're going to try and do that in order. So let's go ahead and do that. So we've got one. So actually this will be pretty easy. 1, 2, 3, 4. So let's go ahead and write those down. And those are in order. We don't skip anything, so we don't have to worry about missing anything. And then in set B, now we have 1, but we've already written 1. So if it's in both sets, that's fine, but we don't need to write it twice. 3 is also, we already have that. And then 5, we include that as well. So notice with union, we take everything that's in either set. So every number, A union B, and let's take a moment and kind of contrast that with A intersected B. The union, we wrote every number that's in either set. With intersection, we wrote only the numbers that are in both sets, the 1 and the 3. And so that's the difference between union and intersection. Let's do another union problem. Our example for number 5, B union C. And so let's go ahead. We got 1. Sometimes a little hard to draw those set brackets. We got 3. And then we're trying to do this in order. We got 1, 3, we got 4. 3 we already have. We got 4. And then 5. I think that covers everything. 1, 3, 4, 5. We'll check that. Yeah, that looks good. So that all the numbers, the union or uniting sets B and C, everything there, 1, 3, 4, and 5. That takes care of everything. And again, 3 is in both sets, but we only need to write it once. Now, we'll contrast that with the intersection of B and C. So union means, again, we write everything that's in either set. So that was 1, 3, 4, and 5. That covers all the numbers that are in either set. But the intersection is only the numbers that are in both sets. That's why it was just the 3 and the 5, because 1's only in set B, 4 is only in set C. All right, again, as we always say, pause, rewind the video, make sure you got a good understanding of that. Now, the last thing we're going to be talking about is the complement of a set. Now, if I give you the description of what a complement is, it may sound confusing at first, but the work is actually very, very simple. So let me go ahead and give you the definition. So a complement, so in this case, B complement, or the complement of set B. So the complement of set B are all the numbers that are in the universal set that are not in set B. And we'll say that again. All the numbers that are in the universal set that are not in set B. You say, well, that's still confusing. Well, here's what you do. If you want to find the complement, so a couple things to mention here. I know this looks like an exponent. It's not. So don't read anything into that. This is just the way they represent the complement of a set. And so let's go ahead, and what we're going to do is write out the universal set. Remember, that was the numbers 1 through 8. And so remember the definition of complement, all the numbers in the universal set that are not in set B. So now we need to eliminate the numbers that are in set B. Well, what's set B? 1, 3, 5. So 1, 3, 5. Now, what's left? 2, 4, 6, 7, and 8. And we'll write that. So we only have that in the set. So 2, 4, 6, 7, and 8. That is the complement of set B. Again, all the numbers that are in the universal set that are not in set B. And the ones that were in set B, we crossed out. So we only have left those numbers that are not in set B. All right, let's do that one more time, this time with set D. So once again, we'll write out the universal set. But this time we're doing the complement of set D. All right, so now D are the numbers 6, 7, and 8. So you probably know what we're going to do now. We're going to cross out 6, 7, and 8. And all the numbers in the universal set that are not in set D, 1, 2, 3, 4, 5. And we'll write that out as our answer. 1, 2, 3, 4, 5. And that's it. All right. So just double checking everything, make sure we covered everything. I think we did. Yeah, I'm very good. Yeah, all right. So that is it for problems 1 through 7 and page 14. Now, page 15, we're getting into the probability aspect of this. And so let's go ahead and erase all this. And what we're going to be looking at here is a Venn diagram. And we're going to be answering some similar questions, but in the context of probability. And we'll explain what all that means. So these are the examples for 8 through 11. All right, so let's go ahead and draw our Venn diagram here. And we label this with an S. We'll explain what that means in a second. We have set A and set B. And set A, we have 1, 2, we have all of this, and we have that there. All right, so now just like we had a universal set, whoop, can't see that, can you? There we go. So just like we had a universal set in the last problem, we have a universal set here. Although, for whatever reason, they call it a sample space, but it's the exact same idea. So S is referring to something called the sample space, which again is the same idea as the universal set. And so let's explain how all this works. So our universe is contained in this rectangle. So all the numbers we care about or we're going to be concerned about in this problem are just the numbers 1, 2, 3, 4, 5, 6, 7, and 8 again. And so that's our sample space. Now, to understand what the Venn diagram represents, let's make sure we understand that. So what numbers are in set A? Well, obviously 1 and 2, but also 3 and 4. Now you might say, well, yeah, but those are also in set B. They are, but they're also in the oval for set A, so we include them for set A. And you might say, well, do we also include them for set B? And we do, because again, they're in both ovals. So what's in A? 1, 2, 3, 4. What's in B? 3, 4, 5, 6, and 7. Now, the number, you say, what about the 8 over here? Well, the 8 is in our sample space. It's part of our universe, if you will, but it's not in either set A or B, and that's how we show that, by putting it outside the oval somewhere else in the rectangle. All right, so let's go ahead and take a look at our first example. We want to know the probability that a number is in set A, and this is for number 8. So I guess we'll work them across here. So the probability that a number is in set A. So not just what numbers are in set A, but what's the probability that a number falls in set A? Well, how do we do probability? Well, probability is our favorable outcomes. In fact, let's go ahead and put that over here. Our favorable outcomes over our total possible outcomes. And so, for a probability of set A, that would be the number of elements or how many numbers are in set A over the total that's in our sample space. So how many numbers are in set A? 1, 2, 3, 4 of them. Remember, we include the 3 and the 4 because they're inside that oval. And so and then the number that's in our sample space is 1, 2, 3, 4, 5, 6, 7, 8. So the probability that a number is in set A is 4 over 8, or 4 out of 8. Now, as always with a fraction, we want to simplify it if we can. These are both even numbers, but so we know that we can divide both of them by at least 2. But let's look at the factors of 4. 1 and 4, and then 2 times 2, and then 8, 1 and 8, and then 2 and 4. So what numbers do these two factor sets have in common? Well, 1, 2, and 4. We want to take the largest. The largest of those is 4. So we're going to divide both of these by 4. 4 divided by 4 is 1. 8 divided by 4 is 2. So our simplified probability that a number is in set A is 1/2. All right, let's take a look at an example for problem number 9. So problem number 9, we're doing the probability that a number is in set B. And set B, again, the probability of that would be the number, the number of elements in set B over the number in our sample space. So in set B, this oval here, we have 1, 2, 3, 4, 5 numbers. Remember, 3 and 4 are in those sets. So 1, 2, 3, 4, 5 numbers. And their sample space, now we don't need to count that again because we already know we're using the same diagram. We already know that there's 8 numbers here, so 5 out of 8. Now, the only factors of 5 are 1 and 5. 5 is a prime number. The only way to multiply to 5 is with whole numbers is 1 times 5. And we'll write out the factors of 8, but we could also just ask, hey, is 8 divisible by 5? It's not. And so that tells us that our answer here is already in simplest form. And notice the only common factor is 1, and we don't simplify with 1 because dividing by 1 is not going to change either of those numbers. All right, so that is our example for number 9. And it looks like we're going to have to write a little bit smaller here for 10 and 11. Let's see if we can squeeze these in here. So for number 10, we're doing the probability of that a number is in the union of A and B. So you say, well, that looks a little more involved. Not really. It's the same idea. It's the number of elements in the union of A and B over the number in the sample space. So remember, union means we take everything that's in either set. So let's go back way over here. And so what's the union? What's everything in either set? Well, 1, 2, 3, 4, 5, 6, 7 numbers. Everything's in the union except 8. So 7 of the numbers are in the union of A and B. And then our sample space is 8. And let's go ahead and put the reducing numbers over here. So the factors of 7 are 1 and 7. 7's another prime number. We already know the factors of 8. And notice that the only factor they have in common is 1, which tells us that this is in simplest form. All right, now, number 11, you might guess already where this is going. We did the union. Now we're going to do the intersection. And let's see, make sure you can see that okay. All right, so the probability that a number is in the intersection of A and B is the number of elements that are in the intersection of A and B over the number that's in the sample space. Let's make that look nicer. All right, so the intersection is the numbers that are in both sets. Now, we've talked about that a little bit already, how 3 and 4 are in both sets. And where the ovals overlap in here, this is the intersection. So how many numbers are in the intersection? Well, there's 3 and 4, so there's 2 of them. So there's 2 numbers in the intersection. And we know our sample space is 8. Now, you might look at this and know already what we can divide by to simplify, but let's go over it. The factors of 2. 2 is yet another prime number. And the factors of 8, we already have those from previous problems. And so the ones they have in common are 1 and 2. The largest is 2, so we can divide both of these numbers by 2 to simplify. 2 divided by 2 is 1. 8 divided by 2 is 4. And so our simplified probability that a number is in the intersection of A and B is 1/4. And that is it. I think also they, let's see, do they ask for the decimal? No. One of the things that we may have done in class, we may do in class, is to convert these probabilities to decimals. If you have to do that, you just divide the numerator by the denominator. So 1 divided by 2 would be 0.5. 5 divided by 8 would be 0.625. And then 7 divided by 8, as we come over here, would be 0.875. Remember, when we're dividing a fraction or converting it to a decimal, we enter the numerator, the top number first, divided by the denominator, and 1/4 would be 0.25. Now, if you don't do that, you're okay. As long as you have the fraction simplified, that's good. But we might be talking about that in class. All right. So that is it for number 11. We have got one more to do, just one more, and we're done. We're almost there. So let's go ahead and erase. Well, let me go ahead and put this in case you want to look at all the examples together. And you can pause there. All right, there's a chance to pause. We're going to go ahead and erase this. And we'll do an example for number 11. Number 11, they want us to use the complement to find a probability. All right, so let's go ahead and read. It says you roll a 6-sided number cube, use the complement to determine the probability of not rolling a 4. All right, so for number 12, we're going to do the probability of not rolling a, what was it, 2 or 3, sorry, 3 or 5. Not rolling 3 or 5. So remember what the definition of complement is. It's all the numbers that are not, in this case, 3 and 5 on our 6-sided number cube. So what numbers are in a 6-sided number cube? Well, 1, 2, 3, 4, 5, and 6. All right, so we're going to use the complement. So all the numbers that are not 3 or 5, so we're going to cross out 3 and 5, and all the numbers that remain are the complement, are not 3 or 5. And so remember, that would be our favorable outcomes, 1, 2, 3, 4, over our sample space, which there were 6 numbers on our 6-sided number cube. And so we have 4 over 6. And we can simplify this. The factors of 4 are 1, 2, and 4. The factors of 6 are 1, 2, 3, and 6. They have 1 and 2 in common. The largest of those is 2. So we're going to divide both of these by 2. 4 divided by 2 is 2. 6 divided by 2 is 3. So our simplified answer of not rolling a 3 or a 5 is 2/3. All right, that is it. So we did go a little fast, especially through the simplifying. But again, of course, obviously this is a video, so you can pause it, you can rewind it, study the examples. As far as finding the factors, what all you're doing here is just asking yourself, what numbers can I multiply to get 6? Or what numbers can I multiply to get 4, which is 1 and 4 and 2 and 2, or for 6, 1 times 6, 2 times 3. You can also, if sometimes if some of these, if multiplication is still a work in progress, you can just Google factors of 4, factors of 6, or factors of whatever number you're looking at. All right, so that's it for the examples for lesson 21.1. Again, pause, rewind the video as needed, and I'm sure you'll do great with the work. So that's it for this lesson. And until the next video, take care and God bless.